Hi everyone. This is lecture 1 of the third module focused on the atmosphere. In this first lecture, we're going to talk about the evolution of Earth's atmosphere, so starting in the distant past, and then make our way to a description of the modern atmosphere. So today, we're going to start with how the atmosphere evolved into what it is today, which is a little bit connected to the origin of the oceans lecture. And identify the difference between the sort of past atmosphere and what the main constituents of the modern atmosphere are. And then, much like we think about the ocean in terms of layers, with the surface and then the deep ocean, we also think about the atmosphere as being layered. And so we'll talk about the characteristics that define the different atmospheric layers. And it might not seem like it, but all of this is building towards an understanding of atmospheric circulation and energy, and there are big connections with the ocean that will start to come about later. So to start with the evolution of Earth's atmosphere, it's just, I think, interesting to start by comparing the atmosphere of Earth versus the atmosphere of some other planets. And I think this is a really cool infographic that shows it. It shows the relative pressures of the various other atmospheres here, using units of atmosphere, where the pressure on Earth is defined as 1 atmosphere. And then it also shows the composition of atmospheres on other planets. So you can see Mercury, for example, has primarily oxygen, but there's also things like sodium, hydrogen, which is kind of cool. Venus is the hottest planet, and it's got atmosphere is 96% CO2. CO2, of course, being a greenhouse gas, explains why Venus is so hot. And then we've got Earth's atmosphere, and then Mars, you can see, and then the gas giants with their primarily H2 based and helium atmospheres. So if you look at, for example, like the pressure of Mercury's atmosphere, you can see that Mercury's atmosphere is way, way, way thinner than Earth's. And Mars has actually lost most of its atmosphere. You can see it doesn't have a lot there. And the atmosphere, the word atmos actually is Greek for vapor, and sphera is Greek for the word ball. And interestingly, a lot of what we know about the atmosphere and other planets and astronomy is typically attributed to Greek scientists, but it's actually North African scientists who, when the Greeks sort of came along to North Africa, brought the Greek and alphabet, which allowed for a lot of things to be written down in Coptic and Egyptian, in the Coptic language to be written in Greek. And so it appeared as if the scholars were Greek, but really the scholars themselves were North African who did a lot of this work. Okay, so going way, 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 way back in time, about 4.6 billion years ago. Note, this is not a real photo. It's a cartoon. That originally Earth was very hot, it was barren, and it was completely waterless. So Earth formed from an accretion process. We talked about this in the origin of the oceans. And it was essentially a really rapidly rotating, hot, barren, waterless planet that was constantly being bombarded by meteorites and comets. There were no continents. There was super intense cosmic radiation and lots of volcanism from this accretion process. And so the atmosphere and hydrosphere, if you can even think of it that way, were quite different than they are now. This, as a refresher, is the present-day atmosphere. And so it's primarily N2 gas with about 21% oxygen, a little bit of argon, and then you can see the trace gases, the carbon dioxide and other trace gases here, given in their mixing ratios. And just a refresher on mixing ratios as units of atmospheric gases. Okay, so Earth's very early atmosphere. So let's think about what was happening back then. The Earth itself formed by accretion of solid materials from the solar nebula. It took about 10 to 100 million years for this process to happen, for where there was actually a solid planet, during which time the moon formed. And a lot of volatile compounds were released, and this is the first sort of atmosphere that Earth would have had, and it would have been a really short-lasting steam atmosphere. So as the accretion slowed down, the heat flux dwindled, and that steam atmosphere rains out to form the ocean, right? So that's a sort of quick guide to how we got an ocean. During this time, as the oceans were being formed, and this was during the Archean, the only source of gases to Earth's atmosphere would have been volcanic activity, and so the main gases would have been CO2, nitrogen, water, and some small amounts of H2. So the early atmospheric composition was completely driven by volcanic outgassing, but this would have been wiped away fairly frequently. So the things that were hitting the planet, these planetesimals, meaning like really, really, really large rocks, would have basically vaporized the ocean and wiped away any atmosphere because of the shock waves. And so you'd have this volcanic activity that would lead to these gases accumulate, and then you'd have a bombardment that was big enough that would basically wipe it all out, and you'd have to start all over. And that would happen until about 3.8 billion years ago. So in summarizing Earth's early atmosphere, any water that was in the atmosphere would have condensed out to form the oceans. The bulk of the CO2 that was in the atmosphere was formed carbonates and sedimentary rocks. And as a result of that water and CO2 going on to other places, it basically left N2 gas to accumulate. So N2 gas isn't the bulk of our atmosphere because it was the largest source. It's the sort of what was left behind when the water and CO2 from volcanic activity went on to other forms. This massive bombardment ended about 3.8 billion years ago. That's what the GA means here, billions years ago. And there's evidence of bacterial life as early as 3.5 billion years ago, which is actually a pretty narrow time frame for life to develop, because it's possible that life could have developed before this time, but this bombardment would have completely vaporized everything, and so there's no way it would have persisted. So once this bombardment ended, it didn't take long before we can see there's evidence of life. The atmosphere is typically invoked in most theories on the origin of life on Earth, and this is one of the big motivators to understand its composition historically, and to understand its composition in relation to other planets' atmospheres, as you know, there's a lot of interest in the development of life on other planets. So noticeably, there's been no mention of oxygen being a component of Earth's early atmosphere. And that's because without photosynthesis, there is no oxygen in Earth's atmosphere. So we've already gone through the primary productivity lectures and everything, so you guys know what photosynthesis is. It's a metabolic process. CO2 and water are used to make organic molecules, and oxygen is released as a product, as a byproduct. Of course, respiration is the opposite, right? And it consumes oxygen. So in order for this released oxygen to actually persist, you have to remove the organic compound in some way so that it can't be respired. So if you hide this organic compounds away, then the oxygen remains. And so it's not just photosynthesis that you need in order for oxygen to build up in the atmosphere. You need photosynthesis and you need the organic carbon or material to be buried. And by burying it, you prevent it from being reoxidized so that this oxygen sticks around in the atmosphere. And so it's actually these two things that lead to oxygen building up in the atmosphere. So the other process is photochemical dissociation. So once you get a bit of oxygen and other products building up, you can get oxygen present in the atmosphere. Once you have oxygen present in the atmosphere and you have sunlight, you can form ozone. And this turns out to be super important because if once you had free oxygen building up and you could form an ozone layer, ozone acts to block incoming ultraviolet radiation. Ultraviolet radiation can be very harmful to a variety of organisms. So it's actually really important to develop an ozone layer. And if you look, this is one of my favorite figures. It's a really old one, but it shows the super long-term evolution of the atmosphere and the ozone layer. And so on the x-axis, we have millions of years before present. And on the y-axis, we have what they call ground level oxygen concentration and ozone as a function, as a comparison to the present level. So this 1 here is the present level. And so this is 100 million years before the present. So that's as recent as this figure gets. And as you move this direction, you're going back in time. So 4,000 million years before the present, that's here. Basically, it's the beginning of the buildup of oxygen in the atmosphere, and that's the solid line. And it shows this solid line and where you first see in the Precambrian some evidence of fossils. That's what these various little things are that it's showing throughout. And this dashed line is the formation of ozone. And so what's interesting is that you have like almost 3 billion years of oxygen being present in the atmosphere, but nothing larger than single-celled organisms are present until ozone is just about its present level. And so it suggests that higher life forms are not capable of being present until there's an ozone layer that's there to protect them from UV light. Because you had billions of years for it to evolve, and they didn't. And then all of a sudden you have an ozone layer and life just flourishes, and you end up with tons and tons of different kind of life forms, which is kind of cool and really highlights the importance of the ozone layer. So biology on Earth, life on Earth, has had a profound influence on the modern atmosphere. Photosynthetic production that outweighs oxygen sinks led to the rise of oxygen. The other way that biology influences the atmosphere is that marine organisms, by consuming CO2 in photosynthesis, they repartition it between the atmosphere, the oceans, and rocks. So there's precipitating carbonate, there's photosynthesis, there's CO2 that then gets buried in the deep ocean. And so without these organisms, CO2 in the atmosphere would be much higher than it is today without biology. And of course now I'm excluding sort of the post-industrial anthropogenic impact on CO2. Obviously, that's a different story. And the other thing, so we talked about this, I don't remember if we explicitly mentioned denitrification, but denitrification is a process in anoxic regions of the ocean that takes nitrate and converts it back to N2 gas. And it is really important because it takes these oxides of nitrogen and puts them back in the atmosphere, because there are some organisms that can take the N2 gas in the atmosphere and use it, and that was that process of nitrogen fixation. So without denitrification, the N2 gas in the atmosphere would have been completely depleted in about 1 billion years. And so these are just a couple of examples of the importance of biology has on the atmosphere. Okay, the next thing that's really interesting in thinking of the evolution of the atmosphere on Earth is what's known as the faint young sun paradox. And you guys, some of you may have watched the video. If not, it's a pretty cool little one. And it's something that's always piqued my curiosity. But essentially, the sun, the luminosity or the strength of the sun has increased by about 40% since the sun formed. And it will continue to do so until it vaporizes everything in the future. So before about 2 billion years ago, Earth's mean surface temperature should have been really low compared to now because of the sun being so much fainter. But the sedimentary record shows that there's been liquid water since at least 3.8 billion years ago, which doesn't really, like, these 2 points don't really coincide with one another. And so it suggests that Earth's greenhouse was way stronger in the past. You would need at least 600 times the present atmospheric level of CO2 to account for the fact that you had liquid water when the planet was so cold. And the reality is that geoscientists and paleoscientists still don't really have a great explanation for this. Okay, so take-home messages from part 1. The formation of the original atmosphere, the sort of Earth's old atmosphere with N2 and CO2, and the water in the ocean was something that happened due to planetary accretion. And as a result, because there's no oxygen in that atmosphere, it would have been a weakly reducing environment. And that must have been the atmosphere when some sort of spark of life happened. Once life got to the point of photosynthesizing organisms, you had this slow rise in atmospheric oxygen because of photosynthesis and organic carbon burial. Don't forget the second part. And as the O2 was rising, the CO2 and other greenhouse gases were declining in some way, shape, or form that we don't understand to compensate for the fact that the sun was getting brighter. So the environment has been sort of fairly stable despite all these large-scale changes. Okay, so from here on forward, we're going to talk about the layers of the modern atmosphere. So to start with, and I'm going to use this diagram on the right the whole time. So this shows temperature on the x-axis in red in degrees C, and at the top x-axis in blue is the pressure. And there's a whole lecture on temperature and pressure later. And then this is altitude. So this is like the opposite of depth, right? This is the surface of the Earth. And then as you move higher in altitude, you're moving towards outer space this way. So the troposphere is the lowest layer of the atmosphere. The word tropos means mixing in Greek, and the troposphere is the sort of well-mixed layer of the atmosphere. And it extends up to the tropopause, which is typically about 10 to 15 kilometers high. Depends on latitude a little bit and time of year. And the troposphere is characterized by decreasing temperature with height. And this is because the surface of the Earth is warmed from the sun. And as you move away from the surface of the Earth, the atmosphere gets cooler. And there's rapid vertical mixing here. And we sort of split the troposphere into two different areas. We refer to the planetary boundary layer, which is the surface to about 1 kilometer. So that's like here, really low. And then above that, we refer to it as the free troposphere. And that's from 1 kilometer up to the tropopause. Okay, the next layer up is the stratosphere. And that's from the tropopause to the stratopause. In this case, the temperature profile has reversed, where temperature is now increasing with altitude. And the reason for that is because there's a lot of ozone in the stratosphere, and this is the good ozone. A lot of times you hear about ozone in the troposphere, and that's the bad ozone, that's the air pollution ozone. But the stratospheric ozone is the good stuff that prevents us from being harmed by UV radiation. And so the ozone absorbs the UV radiation so that as you move up in the stratosphere, it actually gets warmer and warmer by absorbing all that light. The stratosphere has very little mixing whatsoever, and 90% of atmospheric ozone is present in the stratosphere. So the stuff that's the bad ozone is actually quite a small fraction. Moving up again, we have the mesosphere, which extends from the stratopause to the mesopause. In this case, temperature reverses again. So here, temperature decreases with altitude. And that's because there's not really much in the mesosphere. There's nothing there to absorb radiation. And so it just gets colder and colder. And in fact, in the mesosphere is the coldest point in the atmosphere. There's rapid vertical mixing in this region. And then above that is the thermosphere. And again, the temperature profile reverses. And that's because in the thermosphere you have the creation of ions, and the absorption of short wavelength radiation here. And again, you have rapid vertical mixing. We're not going to talk about the mesosphere and the thermosphere a lot. This isn't a course, this is a course about the ocean, so we're going to try to stick to the things that sort of relate to radiation and pressure and things that connect to the ocean. And so it's a little bit the stratosphere, but really for the most part, we're going to stick with the troposphere. So here, this is, I think, a nice way to look at the temperature and pressure profiles a little bit separately, and this is the pressure profile that always makes the most sense to me. Here you can see temperature and pressure in slightly different units. This is temperature in Kelvin and pressure in hectopascals. On the right is the temperature profile, so you can see the troposphere where temperatures decline with altitude, and then the stratosphere, they reverse, and then the mesosphere. And then on the left, you can see the pressure profile in context. And so pressure is highest at the surface, and this is a log scale on the x-axis here, and pressure rapidly declines as you go up in altitude. So that's primarily because when you're on the surface of the Earth, you have the weight of the entire atmosphere sitting on your head, and so pressure is highest. As you go up, if you were to sort of take an imaginary elevator up to, let's say, the middle of the stratosphere, you've got a lot less atmosphere sitting on top of you, and so pressure is a lot lower. So if any of you are familiar with a barometer, it's a frequent tool used to measure atmospheric pressure. And it's a nice way to sort of visualize this idea that there's weight exerted by the atmosphere. And so here you've got mercury, this silver stuff, with an upside down little beaker or test tube. And what ends up happening is the atmospheric pressure pushes down on the mercury and it pushes the mercury up. And so you can measure in inches or centimeters or whatever how much the mercury's been pushed up the tube, and this gives you an idea of the atmospheric pressure. And so you can calculate this directly using the density of mercury. G is the acceleration of gravity, and then H is the height measured by the barometer, and it allows you to calculate the pressure. So if you have one of these barometers with you in various places, you can measure the pressure in various parts of the Earth's surface. And then just another reminder, I think we had this before, that there's some unusual units that we use when we talk about pressure. So mean atmospheric pressure at sea level is defined as 1 atmosphere, which is very useful, but it's also frequently defined as hectopascals and torricellis, and so this just gives you an idea of how to go back and forth. So the take-homes from part 2 here, the atmosphere is divided into lower and upper regions. We define layers of the atmosphere by their temperature profiles, so we're using those inversions in temperature to define the various layers. And we're not going to get much past the meteorology, which is the study of the lower atmosphere, the troposphere, and the stratosphere, but really the troposphere. And we'll talk more in future lectures about how temperature and pressure vary with height in the atmosphere and how we use